your body.
Number 8. Number 8 says, lifting a heavy item in an improper fashion, bending at the waist instead of bending at the knees, sometimes can result in back injuries or back pains. Use the concept of torque to explain why back injuries occur. And you can even see it in the little picture. You can't see it up here on the board, but in your little picture right there. Well, he is doing that, but if you can read a little bit closely, what does it say right there?
Ouch.
So, this is relevant stuff, people. It doesn't get much more relevant than this. He is. Must be. The only explanation. So. All right. So let's take Mr. Ouch. And let's zoom in. Okay. All right. So here's Mr. Ouch. Okay. And here is our rotating object. The rotating object is basically the top half of your body. Okay? Here's your point of rotation, somewhere like around your hip. Okay? Does that make sense? We're talking about this rotation here? Okay? Yes? Okay. That's so disappointing that I don't have an actual video camera on me to demonstrate this. All right. To get you to rotate, something has to apply a force to the top part of your body, right? And generally, if you're bent over like this, you're bending this way, what's applying the force to get your body to start rotating back up this way? Your back muscles, okay? The back muscles that are responsible for that basically attach to your spine right about here, and they're applying a force like this, okay? But what do you see about your lever arm in this case? Not very big. Okay? On the other hand, Benji, kind of dealing with what we were just talking about before, if you're lifting this box, right, that box is applying a force to you, okay? But when you're carrying your arms, it's applying it way out here because that's where it's attached to, like, your spine. Does that make sense? Probably where your arms are, okay? So now, what do you see about the lever arm of that box and the torque it's creating on your body? It's a big lever arm. So if we go here, right, T is equal to F times T times sine of theta, back has a real small lever arm. Box has a much larger lever arm. Okay? Which means if your back is going to create more torque in the counterclockwise direction, right? If your back muscles are trying to make you rotate like this, but the big box is trying to make you rotate like this, okay? Well, if we want the back to win and make you stand up like this, how much force does your back have to apply because of its real small lever arm? It has to apply a lot of force, right? Whereas the box doesn't have to apply. Well, the box can't really apply any more force than gravity's pulling on it. But if your back muscles need to apply more force than they're capable of applying, right, are you going to stand up? No, right? Your muscle is either going to rip, yeah, or, in an extreme case, might pull right off the bone. That's always a fun thing to think about. Right? So it doesn't sound good. Yeah, no, it doesn't sound good at all. You're going to roll it.
Stop before it rips.
Well, if it rips, usually you'll fall back down because you don't have that. You don't have, in the case of this picture, the counterclockwise torque anymore, and the clockwise torque just stays that. Generally, you don't. You go like this. You go like that.
Somebody hold you up?
Oh yeah, so we can hold you up.
Oh, you just hold.
No, well, I mean, once you stand up straight like this, now you have some other muscles to help. But yeah, a lot of times, like when people hurt their back like that, they don't stand up. They just end up all hunched over like that. So. One more weird body thing. So, this isn't a question from your sheet, but it definitely applies to the same sort of thing that we just talked about. Okay. In conclusion, right, bending with your knees, right, allows you to use different muscles. Instead of using your back muscles, now you're using your quads and your hamstrings and your butt, which are a lot stronger than your back muscles. Okay? So that's why you use your knees. So, arm. You have bad knees. You can't look like that too. So, all right, arm. Forearm, right? Upper arm, which is humerus, okay? And then, where's my, it's not even a good thing to laugh about. I mean, so, anyway, where's my anatomy and phys people, right? What is this? That's your bicep, right? Okay, biceps brachii, exactly, okay. Humerus, right? And what are these two? Ulnar radius. Which one's which? Yeah. Alright, anyway.
Did you just ask that because you don't know?
No, I really do know. So,
Sure.
I could take that. Back about 2 years ago. Yeah, take that.
Well, I mean,
Anyway. You're good now. So. Anyway, your arm, bending your arm is a rotation. The bottom part of your arm is rotated. This is the center of rotation. That's your elbow. Okay? In order to get it to rotate, you need to apply a torque to it. The muscle that's responsible for applying that torque is your bicep muscle. Okay? It applies a force to the bottom of your arm, causes your arm to rotate like this. But look at the lever arm on your bicep. Right? How close is your bicep attached to your actual elbow, the point of rotation? Pretty close, right? So is it a very efficient way of creating torque? Are we okay with no?
Yeah.
Okay. Are we okay with no? Yes. All right. So it's not a real efficient way of creating torque because it doesn't have a very long lever arm. Right? How could we make your arm more efficient? Yeah, attach your bicep way down where? By your wrist.
That won't look silly at all.
That would create much more torque, and you could lift a lot heavier things. Okay? But you have a big muscle running here, and that's not awkward and probably not very efficient from
How should you be able to bend your elbow?
Well, I mean, you have another muscle that bends it back the other way.
Right, but
But then how would that, wouldn't that have to work on like,
Unless,
could you really attach it?
unless somehow, like if you, like, you know, unless somehow your tendon ran all the way down here and attached to your wrist on the other side, you know, then, exactly. So, then you could do it, but, you know, that's not how it works. So, somebody must have known something, it's like natural selection based, you know, stuff like that. We ended up this way instead of having like big, you know, muscle with a flap of skin covering
That
it.
doesn't look as ridiculous.
It doesn't nowhere near as ridiculous. So.
I think that timer's longer than that.
You think so? Oh, still got some time left. Yeah.
Hi.
You getting okay.
I like to pretend I'm a robot most of the time. I don't like to think about the inside of my body. That disturbs me.
All right, let's do one more.
Okay, I like this one better.
Yeah, this is fun. Structure.
I like construction.
All right.
Whoa.
You know what?
We have like 2 minutes left.
Oh, we can get some stuff. Actually, this one's good because I get to draw a pretty sweet picture on this problem.
Okay, let's just draw it and then we'll
All right, so number 14 says the arm of a crane at a construction site is 15 meters long, makes a 20-degree angle above the ground. Then the maximum load that the crane can lift is limited by the amount of torque produced at the base of the crane. So we'll start off here. And,
I'm trying not to think about anything.
okay, ground. Oh.
Wow, this picture is totally worth it right now.
There you go. Okay.
Wow, this is insane.
This is turning out well.
Wait, I feel like after we're done looking at this,
the world.
drawing this picture, we should take a gander at that timer.
was up in a minute. So,
It's getting close.
My clock is 6:50 on Friday.
No.
Or you can draw a better one on Friday.
All right.
Practice makes perfect.
True. Maybe we'll do this problem over
Perfect
Friday,
practice.
and then I'll get better at drawing cranes, and you'll get better at doing torque problems.
That doesn't sound like a terrible idea.
But in order to do it over on Friday, we need to do it first today. Yeah. Okay. So,
I think we got this.
A, what is the maximum torque that the crane can tolerate if it can lift a load of 4,000 kilograms? So what is part A asking us for?
T,
The maximum.
whatever that is.
Cow?
Tau. Right? It's asking us for the torque. Okay? It gives us a couple of things. First, it gives us a lever arm, right? It tells us that the crane is 15 meters long. That's going to be our lever arm because that's the distance from the center of rotation. Here's the rotation point right here. Okay? Second, what's the force that's creating the torque on the arm of the crane? It's actually a gravity force, right? And that gravity force is coming from gravity acting on what? The load that it's holding, right? So the force here is just going to be a gravity force times g. Or what did it tell us about the mass of the load? 10 to the third is 4,000 times 5.81. Let's run that through real quick and see what we get.
Oh my gosh. No. How did they use gravity? I would have, but it put a plus sign at the end.
This gravitational force acting here, that's the force that would cause in this case, that gravitational force would cause a rotation like this. Does that make sense? That it would cause like the arm of the crane to rotate downward. Okay? So, but it's the gravity acting on the load that's causing that rotation. If there was no gravity, there would be no force that would cause the arm of the crane to fall down. Does that make sense?
39.
But that means we have to overcome this force, right?
We're
What
at
is it?
39,240.
Okay, we do have to stay with this. Now,
Are you sure it's not?
go on.
Oh, that's
Hey,
not the answer.
hey.
The timer's already done, I know.
So,
Timer's done.
it tells us that the crane makes a 20-degree angle with the ground. So it tells us this is 20 degrees. But is that the theta that we want to use in this problem? That's not the angle between the force and the lever arm. This is the angle between the force and the lever arm, right? So what does this angle have to be?
20 again? Why?
Because
Wait, oh yeah, I got it.
gravity acts straight down, right? So that's going to be a right angle, so that makes this a right triangle, blah, 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 blah. Okay? So that means that theta in this problem is going to be equal to 70 degrees. So then, torque is equal to F times D times sine of theta. Okay? So we got our force,
I got it.
we got our D, we got our theta.
553,100.
No, wait.
Point.
What is it, 103?
103.08.
Okay. But, sig-wise, we'll go here, 5.53, 10 to the fifth.
Good work, everybody.
And then,
I'm
newtons times meters.
Peter.
All right.
How is that
Good
going
day,
to
we're-
Basically, that would be, that's like the most we would have to do to get this. That makes sense.
Oh man, I have friends that are in that.
That would be the maximum torque with that load.